Hello my dear students. Now we will do the experiment number 4 in radio engineering lab. So in this experiment we have to do the observation of analog multiplication amplifier circuit, and to understand the analog multiplication mixer working principle and the spurious interference, to understand the mixture spurious interference. Now you can see there's a basic block diagram of a mixer. There is an RF input and there is a local oscillator input, and both will be mixed and we will get the IF, that means intermediate frequency, that is the base of superhetted and deceiver. So we will get through to this, and that is pretty much important, that these things are important to generate the intermediate frequency, and that is important to the radio engineers. Now according to the working procedure to the board, that is the working procedure, and that is the board in our kit that we use in our lab. That is the board, and in that board there is a sine wave oscillator here in that part, TP4 the RF input, and the analog multiplier mixing unit is there. So you have to make a circuit through multisim. This circuit should have to be made, and after making this circuit we will get the output of it. Okay, and once there are two inputs, first of all the sine wave oscillator input, and second is the signal source input. Here you can see that the RF output 1 is fixed, that is the V local 200 millivolt, and that is 8.7 megahertz. Okay, and that is the local signal input, and that is the FS, the another signal frequency that is given on the P1. That means this is the RF input and this is the local input, I guess. And if you show that is the RF input and that is the local input, now what should we have to be we have to vary through that. Now there is the data table that we have to fill up. That is the local input. We will vary the local input 60, 80, 100, 150, 180 and 200, and get the intermediate frequency from it. How can we get it? Now we will go through to the circuitry. Now that is the analog multiplier circuitry. As you can see here, there are the two units are there. First of all, we have to vary something in the 8.7 megahertz range, the 200 millivolt, that is the oscillator input here. Okay, we have taken the oscillator in the downwards apologies, and the message signal or the main signal, the sine wave oscillator, the main input RF input is there. That's 1 volt, 4.2 megahertz. That is the local input, local peak to peak value input that we have to take. So first of all we have to take a probe here. So that is the 2 volt peak to peak value, and that's the P1. As you can see here, that is in wiring, that is the P1 source, and last that is the RF output, that is the local input. So we have to vary that local input to find out the RF output, and we have to get the difference output of in the oscillator. Okay. So we have to keep one thing very much clear, that is 200 millivolt in the what is that is the 8.7 megahertz. That means the oscillator input. Okay, now that is the 200 millivolt that I have set here. So let's start. That is the that is the RF, but we have taken that the main RF that we have to change the local oscillator, that is the radio. One thing is the radio frequency and the local oscillator, and other is the radio frequency input, that is between 200 millivolt and 8.7 megahertz, and we have to change the local voltage, that is the local voltage of input in the P1 to find out the output difference. And output we have to get the output from there. Now before starting the simulation, here I have to describe one thing that has been built in the op-amp by using op-amp. It's a multiplier circuit basically. So if I have to just Give you an example, the diode has been used here for rectification. So this type of circuits, the diode feedback circuits, they are using in the multiplier section. Both has been multiplied in that point, and at that point output has been given to a buffer amplifier. It's not a buffer amplifier actually, it's a voltage following amplifier. Then it will go through to the same voltage following amplifier to find out the output voltage. Now we have to vary that portion. 200 millivolt and 8.7 megahertz will be the same. The frequency of that particular circuitry, that means if I take this circuitry, the P1 region, 4.2 megahertz, that will be same, that will not change in that particular section. So let us start. Just giving the probes here, so our first value is 60 millivolts to start the study. 60 millivolts. Now start the study. Okay, now the simulation starts. Okay, just stop it and find it out. That is 193, peak to peak is 398.68 millivolt. Here you get this at that point, or you can see that how much changes that matters in that intermediate frequency output. That is the RMS of 42.651 millivolt, and that is the RMS of 141.42 millivolt. If you particularly understand the difference voltage, just think about that, the average voltage part. If you just take in the average voltage part, you will get that there is a difference between these two. The peak to peak voltage is very short, that is in the nanovolt range, and they are in the millivolt range. That means the difference is very short, and all the the resistors are taking as 1 kilo ohm. So just we have to just go through to the graph art section, how that sequences really works. I think split will be better. Now just see how much change that occurs. Let's start the simulation. When the simulation starts, here you can see that there is a gradual change in the output and input. That is the output section. Output section means that is the IF output, intermediate frequency output, and there is an RF input. Here you can see that the RF input is just over like that. If we want to just take quite a bit the value, if we just want to find out the value quite like that, divisions are not so many, so we just widen the division to find out that what does it matters. Access voltage has been changed. Now we can see the changes between that. Now let us stop it. Now you can find it out. There are some spikes around it in the outputs. Okay, and that part of portion is known as the intermediate frequency or frequency rejection, or you can say that the voltage rejections. That means the difference voltage will come upon. The difference between these two, when that is equal to each other, there is no voltage difference. That will be quite a bit similar and very much smaller, that nano voltage, and almost it's a DC, and sometimes it has some spikes in the negative region. Some is high spikes, you can see minus 232.89. It does because of some phase changes that creates, but that is the IF amplifier output in the multiplier circuit. That I have to if I simulate again, just you can see that this kind of sequences will come along. That can be in any there in here there is no other spike. There's a small teeny spike there. So that's all now. So that's the schematic diagram, and you get the graph art section. You will get the value right there, and just changing the values in that portion you can find it out.